Howdy, YouTube. It's that time again. The time being for another topic review as I work my way through the curriculum at the Flatiron School. Now, if you're new to the channel, new to the playlist, or new to me, just whatever, I'm currently a student enrolled at the Flatiron School, which is a coding boot camp, and I'm enrolled in the data science program. I'm in phase 3 of 5 total phases, and I just completed module number 29 out of 31 in this module. There's really only like maybe 12 in the module. It's like one was in phase 1 and the 20s were in phase 2 and so on. You get the point. So I've actually been recording a lot of videos lately. I haven't even posted the module 28 video yet, and I've recorded another like kind of get bash video between this one and that one. So after this, I'm gonna have 3 videos to upload. So I don't know if I'm gonna dump them or like all at once or space it out or whatever. But anyway, should be a relatively short video today. I say relatively because all my videos are like ridiculously long, but it's okay. But this module was like pretty short. I'm gonna go over some things with this module, and then also want to save a little bit of time to talk about. I have discovered some cool things, and I've discovered a cool data set that I think I'm going to use for my milestone project at the end of this phase, which will start in like, maybe like a week or so. So let's get into the topic notebook. Get everything like full screen and whatnot. All right, so module 29, topic review, naive Bayes classification. So we're kind of continuing with the theme over the last several modules, and most of phase 3 has basically been, at first it was like broad strokes of like the calculus and algebra behind how all these models like fit to various data points and that sort of thing. And then this last half of the module has been like an assortment of particular types of classification algorithms. So like the last one was, it's all blurring together now. Wasn't decision trees. That was before the last module, which was, this is gonna bother me now. We did decision trees. This is naive Bayes. What was in between? Let me take a look, because I'm not gonna be able to focus until I find the answers that I'm looking for. Bayes class. K nearest neighbors. Duh. Anyway, which if you've been watching the videos, you'll know what that means. If not, Google can let you know. So all of that to say that naive Bayes classification is just another type of classification algorithm. My guess is that it belongs to a sort of like a family. There's like, because it like, we particularly in this module go over the Gaussian naive Bayes function, and it sounds like there's maybe other types of naive Bayes functions. But anyway, so in the curriculum, this is a little quote from the curriculum, which it says, it basically allows you to develop a belief network taking into account all of the available information regarding the scenario. So basically what the like naive Bayes classification is doing is, it's, say you have like, let's keep it simple, like a binary classification problem. So you're classifying something as either like true or false, 1 or 0 or whatever, like heart disease, for example, or the example that they used a lot was classifying like emails if they're spam or not. So you're calculating like, what's the probability that this observation is this class, so it's a 1 or a 0, true or false, given the probabilities of all these other features in the data. And what makes it naive is that you're assuming that each one of your features, your x's, are I think you call it disjoint events. They're independent from one another. The conditional probability of x1 is independent from the conditional probability of x2 and x to the n and so So that's what makes it naive. And what makes it Bayesian is we're using like Bayesian logic here, right? With this, you can see with like the P notation with like y given da 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 da. So this is, if you're familiar with the Bayes formula, this is that, but it's generalized to, or scaled, whatever, to deal with like multinomial x's, I guess you'd say. This is like, so we have like more than one x here, right? We have like a set of features, and so we're taking the product of, that's why we have the pi symbol here. It's like sigma, but product instead of summation. We're taking the product of the conditional probabilities of each feature, x to the I, given a particular class. So if we're trying to predict if something is true, then we would have one here, or whatever class we're trying to label. Yeah, so if you're familiar with the Bayes formula, I went over that like way back in phase 2. I wasn't really vlogging this intensely at that point, unfortunately. But basically, this is just the typical Bayesian formula modified so that you can have multiple predictors. I wasn't vlogging very intensely, but I was taking heavy notes at that point. So I'm seeing if I can find the Bayesian formula here. Yeah, the probability, that's for dependent events. I'm looking for independent events. Yeah. I don't feel like drawing stuff right now. It's okay. I'll try to do some latex here on the fly. So the probability Bayes formula states that the probability of P, the probability of A given B, is equal to the probability how's my latex gonna work here? Frac of the probability of B given A times the probability of A I wonder if, oh man, I need like I've completely like just kind of learned as I went with like the latex stuff. I need to like spend like an afternoon, like really like hammer it down. Okay, and let me make this like the same size font. Haha! I got it. Okay. The fraction was really like the part that I was wondering if that was gonna work or not. So this is Bayes' theorem for yeah, imagine A is y and B is just like an x. So actually, to make this a little bit more obvious what's going on, we're going to use a little x because in this scenario, x is only one feature. A is y, B is x. Okay. So you can see that we have the probability of y here multiplied the probability of x given y, divided by the probability of x. So the difference being, now that we have multiple features represented by x, we're taking the probability that for whatever, like, man, for Bayes logic drives me up the wall. But it's one of the most interesting things about all this. So you're taking like the product of all of these independent events for x. So those probabilities, I'm actually blanking out now. You follow the product rule. Yes, the product rule. No, because they're looking for a union. Man, I need to brush up on my Bayesian logic. This is really putting me in the hot seat. My point being that this is these two things are the same formula, basically, right? You can see we have like the probability of y and the probability of x. Difference between we're having the probability of like all the x's instead of just the probability of x, right? And because we're dealing with like Bayesian stuff, we have to keep into consideration that these x's are independent in disjoint, not dependent in conjoint or whatever. Same thing with this probability of x of I given y. It's the probability of x given y, but just for each value of x. So this has x of I that represents like x of 1, x of 2, x of 3, x of 4, x of 1, however many features, literally how many columns you have in your data. So that was entirely way too long to explain that whole Bayes thing, but good on us for reviewing our Bayesian algebra, or whatever you would call that. Definitely need to go back and brush up on my Bayes theorem. So, how do you do all that with code? How do you calculate? How do you do this in Python, basically? So we have kind of 5 steps outlined here. First, you're going to pre-process your data like you always do. You're going to import your data from whatever CSV file you have, assuming that you're getting it from a CSV file. If you're dealing with like the datasets library, or some datasets are like built into, like, I think NumPy or stuff like that, or scikit-learn has some built-in datasets. However you're loading your data, load it. I use pandas and usually CSV files. Clear your x and y. You've seen me do this like a ton of times, and then you do your train test split. That's from your scikit-learn model selection module, I think. Just Google train test split scikit-learn, you'll find it. So now you have all these data frames here, right? Or tables, rather. They're not technically data frames because that's pandas. So for each feature, you want to calculate your mean, which is represented by mu here, and your standard deviation, which is represented by our lowercase sigma. I don't know why my syntax highlighting has all this stuff as red. That was weird. So for naive Bayes, it's easier basically if you have your target and your predictors all in the same data frame. So we're putting that all of them back together here on this line, and then we're aggregating, then we're grouping them by their target. So we're grouping all the data. We're basically turning the target column into an index. So 0 or 1, the value of the target column becomes the index for the corresponding columns. And we're going to aggregate it with mean and standard deviation, and that gives us kind of this like layered indexing here. So for age, we have the mean of all 0 classes and the mean for all true or 1 classes, and so on and so forth. So that kind of just gets us all the, we could do like df.describe and like all the, there's a lot of ways you could do this, but this, which is how they did it, the instructors did it in the curriculum, is a pretty nifty way to get all this data that you need kind of packaged in one place for you. Using the aggregation, chaining group by and aggregation together in pandas. So calculate conditional probability of your point estimates for each feature per target class. So basically for every feature, age, sex, CP, I think this was like like stroke prediction or heart disease prediction data was where this came from. So for every one of our like original columns from the original data, not these right here, we're going to take the mean and the standard deviation, plug it into this formula, and we're going to do that for each target class. So we're going to do that for age using like our target class of 0 for our y, right? And then we're going to do that again using 1 for our target class. So you use your mean and your standard deviation of each class for this formula, and you do that for each feature for each class that you're trying to predict. That's a lot in English. It's much more elegant in code. So I have this function written here, which is calculating the point estimate given a particular class. So you pass in a data frame, the string of, which is like the label or the column name of the feature that you are targeting, the feature that you're calculating. So if you're doing this for age or sex or CP, whatever that is, or Trest BPS, beats per second, cholesterol, and probably whatever all that means. You're telling the function like particularly which feature you want to do this for. You give it a particular observation point, so an index in like a row that you want to do this for, and the class that you're trying to predict, which is defaulted to 0, but you can change it to 1 if you want. So all of this is going to return a number right here. Sorry, I almost didn't remember for a second. So it's going to give you the point estimate for that particular feature at that particular observation, which is like the conditional probability of that feature of that observation, if that makes sense. Doesn't totally make sense to me, but it makes enough sense that I can code it, so that's okay. Again, I don't know what's up with the syntax highlighting. Like, I know it's in Markdown, but weird. So now you want to predict, now that you have your point estimates, you want to predict the class for a given observation using your point estimation function. So for this function, we just have to pass in the observation row. Your class probabilities is like we instantiate like an empty list here for your class probabilities. I should really comment my code more so I don't lose my train of thought. So this is your probability for your target. So if you're trying to predict like 1 or 0, this is like your class probability for whatever class you're trying to predict. So now this is iterating through. I'm constantly like arguing with myself about like if I should go like line by line through the code or just show the code because the code's like available on GitHub or whatever. I don't know. So basically, you're going to use your point estimate function inside of this class prediction function, and you're going to calculate your point estimate, and that's going to be multiplied by the class probability, which is this part of the function here. We're kind of going back and forth, creating this numerator right here is basically what's going on. So basically what cprobs is going to be, it's going to be 2 values, and you're going to have the probability of one class, or you're going to have the probability of each class. And so cprobs altogether, if you were to like call like sum on it, then it should equal 1, right? Because if you're dealing with like binomial classes, then if like one class is 0.75, the other class, the probability of one class is 0.75, the probability of the other class has to be like 0.25. So whichever class has the greatest probability after this is all said and done, after you've calculated all your point estimates for each feature and everything, you're then going to select whichever class has the highest probability, and that's what you're going to classify that observation as, which in this case it's 0. Now we want to evaluate the model using some chosen evaluation metric. As you can see here, the Flatiron instructors used accuracy, which made sense for the data we were doing this on. You could use any metric that you would use for any other classification algorithm, recall, F1, ROC curve, whatever. So we create our predictions for our training data and our test data. We calculate our residuals of our training data. We calculate the accuracy of our training data, or our training predictions rather, using those residuals. We do the same thing for our test data. And what we're looking for here is not just if it's as close to 1 as possible, but how different are these scores. So if our training accuracy was like 0.6, but our testing accuracy was 0.9, that would be kind of a red flag. You would be a little suspicious of that test data, and like how well it was sampled would be like my first instinct. But these are pretty close. You got 85% and nearly 83%. So those are pretty close together. That tells me that there's good randomness in the sampling of the training and the test split, as well as it's not a bad model to start with at 85% accuracy. Again, that kind of depends on what you're trying to get out of it, and mainly like what you're trying to like, what kind of answers you're trying to question, what kind of questions you're trying to answer with your model. Sometimes it might be like more sensible for you to prioritize like recall or something else over accuracy. Really, it just depends on like what the question is that you're answering. So what was really cool to me and what really got kind of like the gears turning in my head was we learned a little bit about how to classify documents using this naive Bayes method. So you can see here I'm importing a CSV file as a pandas data frame. I'm getting the probability of each of my classes here. You can see that it's pretty imbalanced. Only 13% of our data is represented by spam. There's a bunch of emails and they're labeled ham or spam. Ham being that it's like a legit email, spam being that it's a spam email. Again, this is like a binary problem. Even though we don't have ones and zeros here, it's still like one or the other, right? So to deal with the class imbalance, we undersample the majority instead of, there's not a whole lot of data to begin with, so we don't want to lose any of our minority data. So we undersample the majority data, which basically means we take whatever like amount of data points we have in our minority, we take only that amount from our majority. So we have a 50-50 split of our data. So that's just dealing with class imbalance. I'm pretty sure I've done that in like gone over that in previous videos. Train test split, get into your target and your predictor variables back in the same data frame. So you have X and Y in the same data frame, but you have still your training, your test splits. It's weird. I wish train test split, it's too bad that they don't have like a parameter you can pass in to, maybe there is, where you could just go straight to train DF and test DF instead of doing all this here. You could save a little bit of coding. Next, the next step would be to discover the word frequency for each target class. So you want the frequency of each word, the frequency that each word occurs in each class. So for all the spam emails, like what's the word frequency of like cash, for example, versus for all the ham emails, what's the frequency of like, hello, or like just every word that occurs in that class, what's the frequency of that word. That's what our code here is sort of figuring out for us. And I'm probably not going to go through this line by line. This is on the GitHub if you're curious. But you should get something like this. You should get some dictionary where it has every key in the dictionary is some unique word for. You have a dictionary of dictionaries. So you're gonna have one dictionary with two keys in it, ham and spam, right, for our two classes. And then as the values of each of those keys, you're going to have another dictionary where each key is each unique word that occurs in that class, and then you're going to have the frequency, how many times that word occurs in that class. So you should get a dictionary like that by the time this finishes running. Yeah. It's the dog over there chewing on his deer antler. You want to get the total corpus word count, which corpus is this weird word I've started seeing a lot around like the NLP and like linguistic circles. So all that means is just like the set of words like in the data that you have, right? Like what is, so you don't want two of the same word in here, right? You want just like every unique word that occurs like in the data, of which we have 5,904. I'm definitely not going to go through this line by line. That would take way too long. But basically, we have a function here called Baggett, which takes in a document, right? And for this particular occasion, I think it was like paragraphs of text. And it gives you the bag of words like for that document, which is like the unique words in that document, and then that's called within this like classify document, right? So this is essentially executing the naive Bayes math, if you will, on this data that we've kind of pre-processed for the purpose of classification. So this makes a lot more sense in my head than it does when it comes out of my mouth, so I'm sorry about that. But that's kind of the point of these videos, is for me to practice this sort of stuff. So, and it's also like I'm constantly trying to decide like what's important to zero in on and what's important to like brush over. But anyway, so you can see like where we're declaring like num and denom and p and like all that. Those are all like parts of our formula here. Our numerator, our p, our denominator, all that stuff. So if you would like to use it, this is a function that does that. It's available on the GitHub. And of course, you want to evaluate the performance of your classifier. To do that, you're going to calculate your residuals, and then you're going to look at, I should have had the value printout for that right there. But looking at like the magnitude of your residuals is one way that you can evaluate the performance of your classifier. Again, like you could use accuracy. There's a lot of different things. There's not like a single right way to evaluate your classifier. And again, it really depends on what kind of questions you're trying to answer with what you're doing. So that's pretty much it for the module today, for module 29. But something else really cool happened when I was getting into that second half of this module, where we were talking about the document classification using naive Bayes. I'm getting a phone call. Hold on. And I feel really bad because that was one of my really good friends, and I just hung up on him. But it's okay. He's got thick skin. Sorry. So we were talking about document classification using naive Bayes, and that got me really thinking about my phase 3 milestone project. And one of the cool things about this project is that the phase 1 project, they gave you the data and like the business scenario, right? The business you were working for and the problem you had to solve and all that. Phase 2, they gave us the data, but we had to come up with our own like business use case. For phase 3, we had to come up with our own data and our own business use case. So I started looking around like Kaggle and stuff for some cool data. Because one of the things they mentioned was like at this point in the program for this milestone project, you really want to start zeroing in on and like on like what you want to do like for a job, like what's like the kind of specialty you want to go into. And for me, the thing that really like strikes my curiosity the most right now is natural language processing. So I found this really cool data set, and I finally figured out how to like handle it, because it comes from this library called data sets, and there's just a bunch of different data sets that you can use within this library. But it was in this like data set object, the same way like in other libraries you have like class objects like specific to that like library. The data set was an object, and so it took me a little bit of figuring out. But basically, I got 6 different languages with 200,000 observations each of Amazon reviews. So these are all like Amazon reviews, and it has like the sentiment for the review, the reviewer ID, product ID, all that stuff, and the review title, the language that it's spoken in, which I need to figure out like what these abbreviations mean, and the product category, and of course you can. So there's like 6 different languages. So this is really cool, and I have to get it approved, but I'm pretty sure that this data will satisfy like the needs for the project, and I have an idea of the classification task I can do for it. There's 6 different languages here, so basically I would train a classifier to classify what language text is in. So it would just look at a random piece of text and it would be able to tell you like which language it is. So that's really cool. I just wanted to bring that up in this video while I had a chance. Yeah. So as always, I don't do this on behalf of Flatiron. But I think Flatiron's really cool, so you should go check it out. Some of the code and like pictures and stuff that I use in these vlogs are Flatiron stuff. So again, credit to them. Go check out Flatiron. It's really cool. Calling it a coding bootcamp doesn't do it justice. We were learning a lot more than just coding. If you're curious about what's going on at Flatiron, I'll have the link to the website below. I'll also have a link to my GitHub if you want to check out my repo for this or any other of my projects I got going on. And if you want to connect with me personally, my link to my GitHub will be down below as well. So until next time, keep on learning, keep on coding, keep on doing cool stuff like that. I'll see you next time.